Hello everyone, my name is Agnes Wansing, and during the next 5 minutes I'm going to tell you something about integrated geophysical-petrological modeling of Greenland with gravity gradients. Greenland is covered with an up to 3 km thick ice sheet, which has a huge potential contribution to global sea level rise during the next decades. One key parameter to model the development of this ice sheet is the sub-ice heat flux, which itself is dependent on the lithospheric structure of Greenland. Furthermore, we have an influence of the Iceland hotspot and the hotspot track, which is poorly known. If we take a look at the seismic assessments of Moho depths in Greenland, we can see that the station coverage is sparse. Furthermore, two studies based on the same receiver function data show Moho depth with up to 11 km difference, as you can see here on the right map. One dataset which is uniform in spatial coverage and data quality are gravity gradients from satellite data. Here we use the gravity gradient data from the XGM 2019 model. The data is calculated at 50 km height from degree and order 11 to 300. We reduced the data about the effect of topography and bathymetry and as well of the ice, which gives us the mass-corrected gravity gradients, which you can see here. For the modeling, we will focus on the V-up component. The method which we use to invert the gravity gradients for the Moho depth is from Haas et al. 2020. The novelty of this inversion is an additional initial dataset, a tectonic regionalisation. The pattern of this regionalisation is used to assign a lateral variable density contrast along the Moho. So the inversion outputs you an inverted Moho depth, but also the variable density contrast along the Moho. The tectonic regionalisation used by Haas et al. 2020 is the global one from Schäfer and Lebedev 2015, which has a lateral resolution up to a degree. For our Moho depth inversion in Greenland, we calculated our own tectonic regionalisation by K-means clustering with 0.5 degree resolution. This regionalisation is based on an updated tomography model from Lebedev and Shelley. Here you can see the inverted Moho depth. It has an RMS error respective to the seismic data points of 8 km. The inverted density contrast varies from 350 to 600 kg per cubic meter. The gravity fit of this Moho depth towards the V-up component you can see here on the right. The RMS error is 1.3 adverse. Next, I will show you some preliminary results of the full lithospheric modeling. For this model, I used an older version of the Moho depth, and therefore the results are preliminary. The software we use is Litmos 3D from Foulier et al. 2009, and the general modeling scheme you can see here on the left. During the modeling, you adjust the Moho depth and the LAB depth to fit your forward calculated fields of the model to the observables. One of these forward calculated fields is the isostatic topography, which then, when it's compared to the real topography, gives you a residual elevation. The same can be done with the density structure of the model, which gives you a residual gravity gradient component. Furthermore, you can take cross sections through the model, here for example from the density, but also from the temperature structure of the model. So to summarize what we have done so far, we created a new tectonic regionalisation for Greenland with 0.5 degree resolution, which is based on an updated regional tomography model. Furthermore, we calculated a new Moho depth model from gravity gradients with a variable density contrast along the Moho depth. We also set up a full lithospheric model for Greenland. For the next weeks, we plan to analyze the impact of single seismic data points on the Moho depth inversion results and to calculate a new lithospheric model, which includes the new Moho depth. This work is part of the Support to Science element 3D Earth, funded by the ESA. Here you can see also the website. If you have questions, please don't hesitate to write me an email.